For centuries, comets and asteroids were seen as wanderers, drifting aimlessly through space. But what if some of these visitors are not aimless at all? In the last few years, 2 objects from beyond our solar system have traced paths so precise, so improbable, that they raise a question we can no longer ignore. Are interstellar visitors deliberately targeting planets? Stay with me. And before we dive in, make sure to subscribe, like this video, and share your thoughts in the comments. Do you think these are chance encounters or deliberate scouts passing through our solar system? What if the stars are not silent? What if, hidden among the countless comets and asteroids, a rare few visitors arrive on paths too precise, too deliberate to be coincidence? In the span of less than a decade, we have seen not 1, but 2 such travellers. They came from beyond the solar system, moving too fast to have been born here, and yet their journeys carried them uncomfortably close to our worlds. The first appeared in October of 2017. Astronomers in Hawaii named it Oumuamua, a word that means scout from afar, the messenger who arrives first. How appropriate that humanity's first confirmed interstellar visitor would carry such a name. It slipped into our system quietly, like a thief in the night, a shard of something ancient, perhaps half a mile long, tumbling end over end at a speed that guaranteed we could never catch it. For just a few short weeks, telescopes tracked its strange glints of light, the wild pattern of its rotation, the impossible push that seemed to drive it away from the sun. And then, as suddenly as it appeared, it was gone, vanishing back into the darkness between stars. A scout that refused to explain itself, a messenger that left its message unsaid. Now, 8 years later, another has come. 3i Atlas, discovered in July of 2025, is larger, brighter, and far more deliberate in its passage. Unlike Oumuamua, which raced through our system and was gone almost before we realised what it was, 3i Atlas lingers. Its course is a grand tour of the inner solar system, weaving close to Venus, brushing past Mars, and swinging by Jupiter in a sequence so precise that the odds of it happening by chance are vanishingly small. Astronomers place the probability at just 0.005%, less than 1 in 20,000. Pause and imagine that. Our solar system is vast, a desert of empty space where most comets spend their lives on the outskirts. But 3i Atlas has not chosen the outskirts. Like Oumuamua before it, it has cut straight through the heart of the system, past the very worlds where life is possible. Oumuamua moved too quickly for us to respond. By the time we realised what it was already leaving us behind forever. 3i Atlas, however, is still here. It slows just enough near Mars to raise suspicion, just enough near Jupiter to suggest intention. Astronomers measure its subtle course changes and whisper among themselves, is this natural behaviour, or the fingerprints of control? Consider the sheer improbability. Imagine throwing a dart not across a room, not across a city, but across the void between stars, and somehow hitting the dartboard, not just once, but brushing past multiple bullseyes along the way. That is the level of precision 3i Atlas seems to display. And then there is the timing. Oumuamua appeared in the very year our telescopes first became sensitive enough to notice such fleeting visitors. It was as though it had waited for us to be ready. 3i Atlas arrives now, exactly as humanity begins to take its first true steps into space, building rockets capable of reaching other worlds, wielding nuclear weapons visible to any observer, and surrounding our planet with a web of satellites that radiate signals across the stars. If these are scouts, then they have arrived precisely at the moment we are most worth observing. 2 visitors, 2 stories, one gone, one still unfolding, and both of them have aimed not at the outer wilderness of the solar system, but at the inner sanctum, the realm of Earth, Mars, Venus, and Jupiter. The odds against such precision are staggering, and yet here they are. What makes this even more unsettling is the contrast between them. Oumuamua was silent, elusive, gone before we could truly understand it. This one is open, lingering, almost theatrical in its planetary flybys. It is as though one was the reconnaissance probe, the quick scan, while the other is the survey mission, more detailed, more deliberate. This raises questions humanity is not yet prepared to answer. If Oumuamua was the first scout and Three-Eye Atlas the second, then what are they searching for? What do they seek? Are they watching our planets or watching us? Are we being measured, tested, or simply marked? And perhaps the most haunting question of all, if two such visitors have arrived within just 8 years, how many more are out there? How many have we already missed? How many are on their way, silently threading their paths through the darkness, each one carrying with it the possibility that we are not merely part of the universe, but participants in something far larger, a cosmic story still unfolding. Let us pause here and reflect on what makes these encounters so unsettling. If Oumuamua and Three-Eye Atlas had merely skimmed the edge of the solar system, we might have marvelled at their speed, noted their origins, and then carried on. But they did not choose the outskirts. Both cut straight through the inner solar system, the region of rocky planets and fragile atmospheres, the region where life is possible. Consider the path of Oumuamua. It entered from above the plane of the planets, passed closest to Earth's orbit on October 14th, 2017, and then curved around the Sun before vanishing into the dark. It was never on a collision course, but its proximity was close enough to raise eyebrows. Out of all the empty space it might have taken, it brushed past the habitable zone. Like an arrow shot through a forest of trees, it threaded the gap cleanly. Now consider Three-Eye Atlas. Its approach is far more precise. Astronomers have tracked it with great care, noting that it will pass within 18 million kilometres of Mars, a cosmic hair's breadth on the scale of interplanetary distances. Later, it swings within 53 million kilometres of Jupiter, perfectly timed for maximum observation. Even Venus is on its itinerary, as though the object has been programmed to gather a complete survey of our neighbourhood. The odds of this happening by random chance are staggeringly low. One study calculated just 0.005%, a probability so small that in the language of statistics, it is considered significant. Significant enough that we must consider other explanations. Imagine throwing a dart blindfolded from miles away and hitting not just the target, but grazing several bullseyes along the way. That is what this new comet appears to be doing, and then we must confront the timing. Oumuamua, the first scout, appeared exactly when our technology had advanced enough to notice it. Before the rise of wide-field telescopes like Pan-STARRS, it would have gone unseen. Three-Eye Atlas II arrives now, as our species has become a radio beacon, as our satellites blanket the skies, as our nuclear fire and spaceflight ambitions become visible across light years. Both arrived not in the timeless void of cosmic history, but precisely as we were ready to recognise them. If this were mere coincidence, it would be astonishing. But if it were intentional, the implications are extraordinary. For if these visitors are targeting planets, then we must ask, what are they looking for? Imagine a reconnaissance mission. A probe sent from afar would not waste its time on the empty regions of the solar system. It would want to study the places where life might exist. Venus, with its dense clouds and greenhouse heat. Mars, with its frozen deserts and hints of ancient rivers. Jupiter, the great giant with its storm-racked atmosphere and magnetic fields. And of course, Earth, the only confirmed world of life, glowing with radio signals and city lights. Each planetary flyby provides a unique angle. Each close approach offers data, the composition of an atmosphere, the spectrum of reflected light, the hum of magnetic fields, even the signatures of technology. By weaving close to multiple planets in succession, the comet maximizes its opportunities. The trajectory looks less like a random path and more like a survey route. And perhaps this is why Oumuamua, the first, seemed so different. It was the quick scout, silent, fleeting, gone before we could focus our instruments. 3i Atlas, by contrast, is the lingering observer, the second pass, the more careful scan. Consider what this would mean. If we are indeed being watched, then our planets are not simply backdrops in a cosmic story. They are test sites, data points, clues about whether life has emerged here and how far it has advanced. 3i Atlas will pass behind the Sun in late October 2025, disappearing from our telescopes for several critical weeks. During this time, it would have an unobstructed line of sight to Earth, a chance to observe us without our ability to look back. Was this timing mere accident, or a carefully chosen window of invisibility? These are the kinds of questions that transform statistics into suspicion. We cannot say for certain, but the pattern, first Oumuamua, then 3i Atlas, both aimed at the inner system, is too precise to ignore. So let us ask directly, are interstellar visitors targeting planets? If so, the implications ripple outward in waves. It means that we may not be alone. It means that reconnaissance, not communication, might be the first step in contact. It means that the galaxy may not be waiting for us to send signals, but may already be quietly measuring us, recording us, testing us. And from that perspective, every planetary flyby becomes more than a celestial curiosity. It becomes a message, not in words, but in action. A demonstration that we are on someone else's map. Oumuamua was the scout, the messenger who arrived first. 3i Atlas is the surveyor, the cartographer of worlds, and together they whisper a possibility that is as wondrous as it is unsettling. That we are not simply drifting alone in a silent universe, but are already part of a larger game. One whose rules we are only beginning to glimpse. The game, if that is what we are witnessing, began with a paradox. In 2017, the first interstellar visitor revealed itself not as a comet, not as an asteroid, but as something far stranger. From the moment astronomers turned their instruments toward it, the object refused to behave like anything we had ever known. Its light was the first clue. As it spun in the sunlight, its brightness rose and fell in wild swings, sometimes 10 times brighter, sometimes nearly vanishing. Such extreme variation had never been seen before in a body of its size. The only explanation was geometry. It had to be unusually elongated, like a cosmic cigar tumbling end over end, or else extraordinarily flat, like a disc glinting as it turned. Either way, it was a shape far outside the catalogue of natural fragments we'd come to expect. Most asteroids are roughly rounded, battered into potato-like forms by eons of collisions. Even comets, fragile as they are, tend toward irregular lumps. But this visitor was something else entirely. Its light curve demanded a geometry so extreme that astronomers hesitated to commit to any sketch. Was it a needle slicing through space? A shard stretched impossibly thin? Or a flat wafer, broad and shallow, like a coin drifting through the void? Nature, it seemed, was not supposed to carve such forms, and its spin was no less curious. Observations showed a rotation of about 7 hours, but it was not the steady spin of a planet turning on its axis. Instead, it tumbled chaotically, wobbling like a baton tossed into the air. That tumble suggested violence in its past. Perhaps it had been shattered from a larger body, twisted by tidal forces near a star. Or perhaps, and here the speculation begins, its tumble was the lingering echo of manoeuvre, an intentional adjustment long ago. If the shape and spin were peculiar, the motion was downright shocking. As the object swept past the sun, its path shifted. A tiny but undeniable acceleration carried it outward, as though something had nudged it. For a comet, this would be no surprise. Comets vent gas when they heat, expelling invisible plumes that act as thrusters. But this visitor showed no such venting. No tail, no coma, no surrounding cloud of dust. The sky remained clear, the object inert, and yet it moved as though guided by a force we could not see. Astronomers scrambled for explanations. One camp insisted it must be natural. even if the theories strained credibility. Some proposed it was a block of frozen hydrogen, evaporating invisibly, producing thrust without a visible tail. Others suggested nitrogen ice, chipped from the surface of some Pluto-like world in another star system. Still others argued for a kind of cosmic dust bunny, a clump of material so porous and light it behaved like a feather in the wind of starlight. Each idea was ingenious, each failed under scrutiny. Hydrogen ice could not survive the long voyage between stars. Nitrogen fragments that large were statistically improbable. A dust bunny would disintegrate before making the journey. And so the anomaly remained. No natural explanation fit the data cleanly, which left room for something more daring. Some scientists began to whisper what others refused to say aloud. Perhaps the acceleration was not geological, but technological. Perhaps we were watching the signature of engineering, a thin sail pushed by the pressure of sunlight, or a probe guiding itself subtly as it passed through our neighbourhood. The light curve, the shape, the absence of a tail, the silent push away from the sun. Together, these details painted a picture that was at least consistent with design. Not proof, but possibility. For the public, the idea of an alien messenger electrified the imagination. For the scientific community, it was divisive. Some argued it was irresponsible to leap to extraordinary conclusions when ordinary physics might suffice, however stretched. Others countered that clinging to weak natural models was no less reckless than considering the artificial. In the halls of academia, papers were published, counterpapers replied, debates unfolded, and still the object moved on, uncaring, slipping farther into the dark. This is perhaps the most haunting part of the story, the brevity of our encounter. The visitor was first noticed in mid-October, and by the end of that year it was already too faint for meaningful study. In only a few weeks, humanity's first confirmed interstellar traveller had entered, puzzled us, and vanished beyond the reach of our largest telescopes. We were left with numbers, curves on graphs, statistical anomalies, and a lingering sense of awe. Picture it clearly, a shard perhaps half a mile long, tumbling chaotically, reflecting sunlight in flashes, accelerating in silence, slicing through the inner solar system and then vanishing forever. A first contact not in words or signals, but in impossibility. What are we to make of such an object? If it was natural, it shattered our assumptions about what fragments the galaxy can create. If it was not natural, then we glimpsed something profoundly alien. A relic, a derelict, perhaps still active. Was it a scout confirming that life had taken root on this blue planet? A probe cataloguing the resources of our system? Or only a shard of some long-dead civilization, drifting endlessly without mission or memory? No one can say. The window closed too quickly. Our instruments, still limited, caught only fragments of the truth, but the impossibility of the first scout remains, derived not as a simple rock, not as an ordinary comet, but as a riddle, a challenge, a whisper that the cosmos holds secrets we're only beginning to notice, and if impossibility was the first move, then what should we expect of the second? The messenger had slipped away into the dark, but the ripples it left behind were only beginning to spread. In the weeks after its discovery, observatories across the world pored over the data, chasing the fading trail of light. Each measurement confirmed the same unsettling truth. This was no ordinary fragment of ice and rock. And so began the struggle to explain the inexplicable. Science, by its nature, seeks the natural first. Astronomers knew they had to fit this traveller into familiar categories. The simplest answer was to call it a comet, but a comet with no tail, no gas, no haze. If it was a comet, then it was unlike any we had ever seen. Others labelled it an asteroid, but asteroids do not accelerate on their way out of the solar system. The categories broke down almost immediately, and so a series of hypotheses emerged, each trying to rescue the data from the jaws of impossibility. Some argued it was a hydrogen iceberg. Hydrogen, evaporating invisibly, could provide thrust without leaving a visible trail. but hydrogen ice is fragile. It could never have survived the billions of years required to drift from another star to ours. Another camp proposed nitrogen ice, a shard chipped from a frozen exoplanet long ago. But again the odds strained belief. To produce a shard that large so far from home and have it survive intact across interstellar gulfs? Possible, but vanishingly unlikely. Then came the dust cloud hypothesis. Perhaps this was not a solid body at all, but a loosely bound cluster of particles, a cosmic dust bunny so porous that it responded to sunlight like a sail. Yet a structure that fragile should have unravelled in the cold and the collisions of space. Instead, the visitor held together, spinning in defiance of such fragility. Each idea was ingenious. Each failed under scrutiny. The debates grew heated. To some, forcing the object into a natural box, no matter how awkward the fit, was safer than facing the alternative. To others, clinging to inadequate models was an act of denial. If the data did not fit the categories, perhaps it was the categories themselves that needed revision. It was in this atmosphere that one voice grew louder than most, Harvard astronomer Avi Loeb. He argued that the simplest explanation was that the acceleration came not from invisible ices, but from sunlight itself. The visitor might have been a thin sheet, a light sail, designed to catch radiation pressure the way a ship's sail catches the wind. Such technology had already been imagined by humans, even tested in small ways. Why not elsewhere? Why not long ago? Loeb's proposal was bold and it split the community sharply. Some dismissed it as reckless, a leap into science fiction. Others admitted reluctantly that it was at least consistent with the observations. In interviews, Loeb compared the resistance to denial itself. If you walk into a living room and see an unusual object on the carpet, you can insist it must be natural debris, or you can admit you don't know. And sometimes, not knowing is the most honest answer. The debate spilled beyond academia into the public. For a few months, the impossible object captured headlines worldwide. People asked the same questions astronomers were afraid to answer. Could it have been a probe? Could it have been sent intentionally? And if so, what did it see? What did it learn? What would come next? Yet the data stream dried quickly. By the start of 2018, the visitor was too far and too faint for further study. All we had left were a handful of light curves, velocity measurements, and a list of contradictions. For some scientists, that was enough to file the matter away, unsolved but not unthinkable. For others, it became the spark of something larger. A reminder that the cosmos is not only stranger than we imagine, but stranger than we can imagine. Let us pause here and consider what this moment meant for human knowledge. For centuries, the skies had offered only predictable patterns. Planets circled, comets flared, asteroids wandered. Even the chaos of impacts and collisions still fit within natural laws. But the first interstellar messenger broke the pattern. It arrived from beyond, stayed briefly, and left behind a trail of paradoxes. It was the first object we'd ever seen that seemed to whisper, "Your categories are not enough." The human response was telling. Faced with the unknown, some clung to the safety of the familiar, insisting that nature must still hold the answer, even if that answer eluded us. Others embraced the unknown, willing to entertain possibilities as radical as alien engineering. Between them stretched the wide field of uncertainty, the recognition that, in truth, we did not know. And in that uncertainty lay the awe, for perhaps the greatest gift the first scout gave us was not answers, but humility. It reminded us that the universe does not owe us explanations, that sometimes the sky will send us riddles, and we must learn to sit with the riddle itself. The debates continue even now. New models are proposed, old ones refined. Hydrogen ice, nitrogen shards, fractal dust, light sails, derelict probes. Each theory has its advocates. None can claim victory. The messenger has long since vanished beyond our reach, leaving us to argue over shadows on a wall. But the impact was real. Astronomers began to speak differently about interstellar objects. If one had appeared, more must exist. If one could defy categories, others might do the same. The impossible object had cracked open the door to an entirely new branch of astronomy, the study of messengers from beyond. And then, as if to prove the point, the second arrived. Here was confirmation that the first was no fluke, that the cosmos was not content to leave us with a single mystery. Less than 2 years later, another visitor swept into our system. More conventional in appearance, yes, but its very presence deepened the paradox. For it meant that the galaxy might be filled with such travellers. It meant that our skies may host more scouts than we dared imagine. But before that second arrival can be understood, we must linger for a moment longer with the first. For the first was not merely an object. It was a challenge, a statement, a whisper in the silence of space that said, "You are not alone in being observed." The impossible object was the opening move, and though it has slipped away forever, it has left us with a question that refuses to fade. What kind of intelligence leaves riddles in the sky, and what will its next move be? When the first interstellar scout vanished into the dark, astronomers were left with little more than questions. Was it a comet with invisible exhaust, a shard of frozen nitrogen, or something far stranger? The debate might have stretched on for decades, circling endlessly around incomplete data. But less than 2 years later, the cosmos delivered a surprise that changed everything. On the night of August 30th, 2019, in a small observatory in Crimea, an amateur astronomer named Gennady Borisov was scanning the skies with a homemade telescope. He had built it himself, a patchwork of mirrors and lenses tuned for deep sky watching. That night he noticed something unusual, a faint smudge of light moving against the background of stars. At first, it looked like another comet. But as he tracked it night after night, its path became clear. This was no ordinary object. Calculations confirmed it quickly. The orbit was not bound to the sun. Like the messenger before it, this new body had come from beyond, travelling on a path that cut through our system and would never return. It was named 2I Borisov, the second interstellar object, discovered not by a space agency or a great observatory, but by a backyard astronomer gazing through a telescope of his own making. Already the story felt poetic. The first had been caught by automated surveys, sifted from gigabytes of digital data. The second was spotted by a single human eye, looking directly at the sky. It was as though the universe wanted to remind us that discovery belongs not only to machines, but to the people who still spend long nights searching the stars. And the second visitor looked at first like a gift of reassurance, for unlike the first, Borisov behaved like a comet should. It had a visible coma, a halo of gas and dust boiling off as it neared the sun. It displayed a clear tail, streaming outward like a banner carried on the solar wind. Its chemistry, studied with spectrographs, revealed the familiar fingerprints of ices found in comets within our own system. Water vapour, carbon dioxide, cyanide. It looked in short like the interstellar cousin of the countless comets we already knew. To many astronomers this was a relief. At last, a visitor that fit a category. No cigar shapes, no tumbling mysteries, no invisible accelerations. Here was the data they could trust, the curves they could model, the physics they could understand. Borisov was the normal one, the baseline that proved interstellar comets could indeed resemble our own. And yet, normalcy is never so simple. Because if Borisov was what an interstellar visitor should look like, then what did that make the first? The contrast was striking. The 2017 object had been dark, tailless, a silent shard that slipped away too quickly. This object was luminous, gaseous, generous with information, hanging in our skies for months of steady observation. The two messengers, arriving only 2 years apart, seemed to define opposite ends of a spectrum. And that contrast forced a new question. If the second was a natural comet, the kind we expected, then how extraordinary was the first? The odds of detecting even one interstellar traveller in a human lifetime had seemed remote. Detecting two in such short succession suggested that our galaxy might be full of them, drifting silently between stars. But if so, why had the first looked so unnatural, so anomalous, so impossible? For months, telescopes around the world locked onto Borisov. The Hubble Space Telescope captured images of its fading tail. The Atacama Array in Chile detected the chemistry of its gases. The comet was studied in more detail than almost any other visitor in history, and each result confirmed the same thing. This was a comet like any other, except it wasn't from here. From another star system altogether, Borisov had carried with it the frozen chemistry of its birthplace. In its dust and gas were clues about the conditions under which it had formed, billions of years ago, around a different sun. To hold in our instruments the chemical fingerprints of another planetary nursery was astonishing. For the first time, we had tasted the raw material of alien worlds. Pause here and consider the symbolism. The first scout left us only questions. The second brought answers, but answers that made the first all the stranger. It was as though the cosmos had offered a deliberate comparison. Here is what a natural visitor looks like, and here is the anomaly you saw before. Can you see the difference? Do you understand why the first refuses to fit? Some saw reassurance in this. The universe was confirming that most interstellar debris is ordinary. Shards of ice, tails of dust, cousins of our own comets wandering the galactic tides. The first scout, then, could be dismissed as an outlier, a statistical freak. Others saw the opposite. By offering us a clear baseline, Borisov made the 2017 object stand out all the more. In science, anomalies matter only when you can compare them. And now we had a comparison. In the glare of Borisov's tail, the impossible nature of the first messenger became undeniable. For months after its discovery, the second interstellar traveller hung in the night skies, a faint but steady glow that telescopes around the world tracked with relentless attention. Where the first had vanished in weeks, the new one lingered for months, a moving laboratory in the heavens. Every instrument that could be turned upon it was, and slowly, piece by piece, it revealed its secrets. The chemistry was the first revelation. Spectrographs split its light into bands, revealing the fingerprints of familiar elements: water vapour, carbon monoxide, cyanide. Nothing exotic, nothing impossible, but precisely what one would expect from a comet. It was a portrait of normalcy, and yet extraordinary in its origin. Here, in our telescopes, was the frozen chemistry of another star's nursery. The dust it shed carried the same story. Observations revealed grains rich in carbon, similar to those in our own comets, but subtly distinct in ratios. It was as though we had scooped a handful of soil from an alien garden. For the first time, we were studying the raw ingredients of a world not born of our sun, but of another star entirely. Think of the implications. For centuries, humans had speculated about the planets of other stars. Only in recent decades had we begun to detect them with certainty, through the subtle dimming of transits or the wobble of stellar light. And now, here was physical material drifting past us, carrying the signature of alien worlds. The cosmos had not only confirmed the existence of other planetary systems, it had delivered a sample of their chemistry directly into our reach. This was more than symbolism. It was data, hard and measurable. Borisov's composition confirmed that the processes shaping comets are not unique to our sun. Across the galaxy, wherever planets form, ice and rock gather in frozen reservoirs, waiting to be scattered into the dark. The galaxy, in other words, is fertile with the seeds of comets. And if comets are everywhere, then the water, carbon, and organics they carry may also be everywhere. Yet even as this traveller reassured us with its familiarity, it sharpened the paradox of the first. Because if Borisov was what we expected, a glowing tail, a chemical cocktail of ices, then what truly was Oumuamua? The contrast was undeniable. One gave us answers, the other left us only riddles. astronomers began to speak of the two as bookends. The 2017 messenger was the anomaly, the rule breaker, the one that refused to show its hand. The 2019 comet was the confirmation, the baseline, the one that proved interstellar visitors really can look like the ones we know. And between them stretched the mystery. The cosmos had not only given us two objects in quick succession, it had given us a comparison. Pause here and reflect on the odds. Before 2017, no interstellar object had ever been confirmed. Then, within the span of 2 years, two arrived. What does that suggest? Perhaps they are far more common than we ever guessed, and only now are our instruments keen enough to detect them. If that is true, then hundreds, perhaps thousands, may pass through our skies unseen each year. The galaxy may be teeming with messengers, slipping silently between stars, most too faint for us to notice. And yet, if they are common, then why was the first so strange? Why, out of all the possible shapes and chemistries, did our first glimpse turn out to be the outlier? Why was our introduction to the galactic tide not reassurance, but paradox? Some saw intention in this. Perhaps the cosmos had given us the anomaly first to ensure we would pay attention. Perhaps the first was the scout precisely because it would resist explanation, force us to confront the limits of our categories. And only then, once our curiosity was inflamed, did the second arrive to show us the ordinary, the baseline against which the extraordinary would stand out. Others argued that this was projection, human meaning placed upon random chance, but the timing still stung. The first arrived just as our telescopes became capable of finding it. The second arrived just as we were still reeling from the first. Coincidence, perhaps, but what a curious coincidence. In the quiet halls of observatories, debates flourished. Was Borisov proof that the first was natural after all, simply a statistical outlier? Or was it proof that the first was not natural, by contrast so severe it only deepened the anomaly? The data could not settle the argument, instead it sharpened it. The second messenger also carried a lesson about perspective. From the ground it appeared faint, a blur of light against the black. But through the Hubble Space Telescope, it revealed itself as a delicate wisp, a thread of dust unspooling across the stars. It was fragile, transient, doomed to disintegrate as it passed. And yet in that fragility was its gift, the chemistry of another star system laid bare for us to measure. It is easy to forget how extraordinary this was. For the first time we were studying alien material not through theory or imagination, but directly, through photons captured by our instruments. It was as though a message had been bottled billions of years ago in another ocean, and by sheer chance the tide had washed it to our shore. And so, by the end of 2019, humanity had two interstellar messengers to consider. One was silent, angular, impossible, leaving us in wonder. The other was luminous, fragile, reassuring, leaving us with data. Together they formed a pair, opposites, complements, perhaps even partners in some larger design. If the first was the riddle and the second the reference, then what do we make of the pattern? Is the galaxy filled with billions of such fragments, scattering endlessly across the stars? Are these visitors mere accidents of gravity, or are they scouts and surveyors woven into some grander game? The answers were not forthcoming, but the pattern was undeniable. Twice in 2 years the silence of the stars had been broken by travellers from beyond, and with the arrival of the second, the mystery of the first only deepened. What we had once imagined would be a rare curiosity had become a field of study unto itself. Astronomers began to speak not of if, but of when the next one would arrive. And with each new visitor, the questions would grow sharper, the stakes higher. For every object from beyond carries with it not only data, but possibility. And so, as Borisov faded into the dark in early 2020, the story did not end, it had only just begun. Because two visitors in such short succession demanded theories, demanded explanations, demanded meaning. and in that demand astronomy shifted. Theories would multiply, speculation would blossom, and the impossible would no longer be dismissed so easily. The second messenger had not solved the paradox, it had deepened it. As the second traveller through the cosmos, luminous yet everyday, receded into the void, the arguments only deepened. The contrast between the two messengers demanded explanation. One had conformed to every expectation of a comet: tail, gas, chemistry. The other had violated them all. If both were natural, then nature was far more varied than astronomers had believed. If one was not, then we were forced to consider possibilities that reached beyond geology. The effort to contain the mystery began with the most conservative path: the unusual acceleration of the 2017 object. The subtle push outward from the sun was the puzzle that demanded an answer. The simplest way forward was to assume sublimation, as with any comet. Gas vents like tiny thrusters. The problem was that no gas had been seen. The solution some researchers offered was that the gas was invisible. A body made of frozen hydrogen could sublimate without leaving a visible signature. The hydrogen iceberg hypothesis became the first serious contender. It carried an elegant simplicity. A block of hydrogen ice struck free from a distant molecular cloud could drift between stars, intact in the deep cold. Near the sun, its surface would evaporate, releasing a push strong enough to account for the odd acceleration. But elegance gave way to fragility. Hydrogen ice is the most delicate of solids, vulnerable to even the faintest starlight. The journey of millions of years through the galaxy would strip it away long before reaching us. The hypothesis collapsed under its own timescale. The next candidate was nitrogen. Pluto and other icy worlds in our solar system carry great sheets of frozen nitrogen on their surfaces. If such a world in another star system suffered a collision, shards might be flung outward into interstellar space. A nitrogen fragment, hundreds of meters long, could survive longer than hydrogen, and nitrogen sublimation could explain the acceleration without producing a bright tail. On paper, this seemed plausible, but the odds proved hostile. To match the data, one needed not only a nitrogen shard, but a shard of very specific dimensions, and to explain the sheer chance of seeing such a fragment as our very first interstellar visitor, collisions would need to be common on a galactic scale. Catastrophes producing shards that size would have to happen often in planetary systems across the stars. The numbers demanded a universe overflowing with nitrogen shards. No such evidence exists. The explanation strained credulity. Some astronomers pushed further from convention. Perhaps the object was not a solid block at all, but an ultralight structure. The Dust Bunny model proposed that it was a clump of grains, bound together so loosely that its density was lower than any rock, lower even than aerogel. Such a porous structure could be nudged outward by the faint pressure of sunlight itself. In this model, the acceleration required no tail, no venting, only a featherweight geometry. But fragility became the undoing once more. An object so delicate should not have survived the journey between stars. Interstellar space is not empty. Dust grains collide, cosmic rays strike, tidal forces stretch. A porous cluster would have disintegrated, shredded into mist long before reaching us. And yet the visitor arrived intact, tumbling but whole. There was also the tidal fragment hypothesis. A planet drawn too close to its star could be torn apart by gravity, its body shredded into elongated shards. Ejected into interstellar space, those shards might drift for millions of years before encountering another star. The strange shape, the chaotic spin, even the lack of a tail could all be explained by catastrophe on such a scale. Again, the obstacle was probability. How often do planets fall into such fates? How many elongated shards must drift through the galaxy for us to have caught one so soon after beginning serious surveys? The statistics did not favour coincidence. One by one, the natural hypotheses faltered. Each stretched possibility to its breaking point. Each could be imagined, but none could be demonstrated. The hydrogen block was too fragile. The nitrogen shard was too rare. the dust cluster too delicate, the tidal fragment too improbable. The debates revealed a deeper unease. Science demands caution, and extraordinary claims require extraordinary evidence. But here the evidence was scant and the anomaly glaring. Every natural model bent physics further than most were comfortable with. And in trying to hold to safety, astronomers found themselves describing a cosmos full of hydrogen bergs that could not survive, nitrogen shards that should not exist, dust clusters that should not endure, and tidal shards produced by catastrophes that cannot be common. The unease spread because the first interstellar object should have been ordinary. Statistically, it should have looked like Borisov, a glowing comet, a cousin of those we already knew. Instead, it looked like nothing we had ever seen. To explain it naturally required contortions of physics that strained belief. By the end of these debates, the scientific community had reached no consensus. Papers proposed, papers refuted, conferences filled with speculation. What endured was not agreement, but discomfort. The first visitor had left us with data that resisted every model. The second had provided reassurance, but in doing so had sharpened the contrast. What if the first messenger truly was an outlier, the statistical freak that appears once in a billion? That was one way to reconcile the paradox. But another possibility lingered in the silence. If the natural theories were unsatisfying, perhaps it was because nature was not the full story. Perhaps the acceleration, the shape, the survival, the silence, all were signatures of something else entirely. That possibility, once unthinkable, was beginning to creep into the conversation. As natural explanations faltered, a new kind of theory began to creep into the conversation. One that had hovered at the edges of thought since the discovery, but that most scientists had been reluctant to voice. If geology could not account for the first interstellar visitor, then perhaps technology could. The idea that the object might be artificial began with its acceleration. The subtle push away from the sun could be explained if it were not a block of rock at all, but a thin sheet, a sail broad and light, catching the faint pressure of sunlight. In human laboratories, the concept was already familiar. Engineers had tested solar sails, deploying reflective sheets that rode on photons as sails ride on the wind. Our own prototypes had been small, fragile, confined to the near-Earth environment, but scaled up and hardened for interstellar travel. Such a device could cross the galaxy. A light sail would explain both the acceleration and the unusual geometry suggested by its brightness. A thin, flat structure would flicker as it turned, flashing bright and dim in alternating rhythm. Its mass would be so low that sunlight itself could alter its path. To many, this seemed at least consistent with the data. But to suggest this was no longer to remain in the safe territory of comets and asteroids. It was to cross the line into engineering, and into the possibility of alien design. Some framed it conservatively. Perhaps it was not functioning at all, but merely a relic, a fragment of technology from long ago. A derelict sail drifting silently, abandoned by whatever civilization had built it. Space is vast and time unkind. Perhaps we were not seeing an active probe, but the remains of one. A husk, a fossil, carried across the stars by momentum alone. Others dared to go further. What if it was still active? A reconnaissance probe sliding through planetary systems, gathering data, transmitting it back to distant masters. Its lack of emissions could be explained as stealth, or as a design so advanced it evaded our primitive instruments. Its fleeting passage near Earth could be interpreted not as accident, but as intention. For astronomers trained in caution, these suggestions were uncomfortable. To some, they bordered on heresy. But the power of the artificial hypothesis lay not in certainty, but in dissatisfaction. Every natural model had faltered. The artificial model, while extraordinary, at least did not require impossible icebergs, implausible shards, or fragile dust clouds. It explained the anomalies with a single leap. It was not natural at all, The controversy was immediate. Academic journals filled with rebuttals. Conference halls buzzed with heated debate. Many dismissed the notion outright, pointing out that extraordinary claims require extraordinary evidence, and the evidence here was thin. A single object observed briefly with no emissions, no signals, no obvious technology. To call it alien, they argued, was to abandon rigour for fantasy. And yet, in the public imagination, the idea took root. For months, headlines around the world declared it might be a probe. To ordinary people, the mystery of a visitor from another star carried its own romance. If it looked unnatural, why not entertain the possibility that it was? For once, the public appetite for speculation outpaced the scientists. In this way, the first interstellar object did more than puzzle astronomers. It revealed the rift between scientific caution and human curiosity. In the cautious halls of academia, the artificial hypothesis was kept at arm's length. In the collective imagination, it became the most compelling explanation of all. There were even practical echoes, projects like Breakthrough Listen, dedicated to the search for extraterrestrial signals, briefly turned their instruments toward the traveller, scanning for radio emissions. None were found. But the very act of listening marked a change. It was the first time humanity had treated an interstellar object not only as a geological curiosity, but as a potential artifact. The absence of evidence did not erase the question. If it were a probe, it might not transmit at all. If it were a relic, its silence would be expected. If it were stealthy, its purpose would be to avoid detection. The silence told us little. What it left was possibility. The possibility that the galaxy may be seeded with such artifacts, drifting through systems as part of a network of reconnaissance. The possibility that civilizations too old to speak may still leave behind relics that wander forever. The possibility that our first interstellar contact had already happened, not with a living intelligence, but with its machine, its fragment, its echo. Among scientists, the artificial hypothesis remained the minority view, but it refused to vanish. Each time a natural model faltered, the possibility of technology returned, waiting in the wings, and in the minds of many, it remained the explanation that fit the data most cleanly, if one was willing to entertain it. The debate itself carried its own revelation. For centuries, the question of extraterrestrial intelligence had been confined to speculation about signals and radio messages. Now, for the first time, the possibility had intruded not as a call, but as an object. A physical body tumbling through our skies, defying our categories. Even if natural, it had forced us to consider technology as part of the conversation. The first scout had arrived as a riddle. The theories we built around it revealed more about ourselves than about the object itself. In the insistence on naturalism, we saw the discipline of science. In the whispers of technology, we saw the hunger for meaning. Between them stretched the uncertainty that defines our age, caught between wonder and caution, between the comfort of models and the seduction of possibility. The messenger was gone, leaving only its data and its silence. But in its wake, it had ignited the first serious debate in modern astronomy about whether we had glimpsed alien technology. The idea, once confined to science fiction, had stepped across the threshold into scientific journals and public discourse alike. And that may have been its greatest gift. Not answers, but permission. Permission to consider the extraordinary, to wonder whether the stars might not be silent, but alive with scouts, surveyors, and relics. Theories in the dark multiplied. Some held fast to icebergs and fragments. Others leaned towards sails and probes. None could prove their case. But all agreed on one point. The universe had shown us something unexpected, and it would not be the last. Because the silence had already been broken. Once the first scout arrived, once the second confirmed the pattern, astronomy could never return to its old assumptions. The debate had only begun. Now, in 2025, humanity has recorded 3 confirmed visitors from interstellar space. The first, Oumuamua, in 2017, swift, silent, impossible to categorize. The second, 2I Borisov, in 2019, luminous, chemical, and reassuringly comet-like. And now, 3I Atlas, discovered in July of 2025, brighter, larger, and on a path that has sparked as much suspicion as it has fascination. Any one of these objects might be dismissed as coincidence. Together they begin to resemble a sequence: a scout, a sample, and a surveyor. 3 distinct roles, traced not in theory but in the orbits written across our skies. Oumuamua set the tone by passing straight through the habitable zone, brushing close to Earth's orbit before curving around the Sun and vanishing forever. It didn't linger, it didn't explain itself. It simply appeared, broke the rules of comets and asteroids, and left us wondering. Then came 2I Borisov, the second messenger. Unlike the first, it looked and behaved like a textbook comet, venting gas trailing a luminous tail. Its chemistry was familiar: water, carbon monoxide, cyanide. Yet its very arrival, only 2 years later, felt improbable. 1 interstellar object might be luck. 2, so quickly, suggested something else was at play. Now we turn to 3I Atlas. From its first orbital solutions, astronomers noted how unusual its path was. Rather than grazing the outer system or slipping by unnoticed, its trajectory carries it close to multiple planets in sequence. Models show a flyby within tens of millions of kilometers of Mars, later a passage near Jupiter, and even an encounter that brushes past Venus. None of these are impacts. All are close approaches and the kind that maximize observational opportunities. One probability estimate placed the odds of such a path occurring by chance at just 0.005%. In statistical terms, that is significant. Imagine throwing a dart from light years away and not only hitting the board, but grazing several bullseyes in order. That is the improbability of 3I Atlas's planetary tour. The most provocative detail is what happens as it passes near the Sun in late 2025. For several weeks, its orbit will place it on the far side of our star, relative to Earth. From our perspective, it vanishes into solar glare. But from the object's perspective, Earth is fully illuminated, radiating light, heat, and electromagnetic noise into space. To those who see intention in its orbit, this is the perfect vantage point. We cannot observe it, but it could observe us. Of course, astronomers are quick to caution. These are modelled trajectories, not evidence of intent. Orbital mechanics are precise, but coincidences do happen, and yet when placed beside Oumuamua's precision cut through the habitable zone, and 2I Borisov's sudden reinforcement that such visitors are real, the suspicion lingers. 3 objects in 8 years, 2 of them threading directly through the inner system, 1 of them sweeping past planets in sequence. The targeting question is no longer fringe speculation. It is whispered in observatories, debated in conference halls and imagined in millions of minds worldwide. Are these paths random debris or reconnaissance? If the 3 visitors are chance, then probability has played a trick of cosmic scale. Before 2017, no interstellar object had ever been confirmed. Now 3 have come, each carrying implications larger than itself. If they are not chance, then we may already be living under observation. Patterns are what make science possible. They allow us to move from noise to signal, from chaos to meaning. The pattern traced by these 3 messengers has a rhythm too deliberate to ignore. First, an impossible scout, then a luminous sample, now a surveyor whose trajectory skims key worlds. Whether by coincidence or by choice, the sequence resembles reconnaissance. This possibility forces us back to the Drake equation, the attempt to estimate the number of intelligent civilizations in our galaxy. For decades it was a thought experiment, a balance of guesses. But if even one of these visitors proves to be artificial, then the equation collapses into certainty. The galaxy does not merely host civilizations. At least one has sent instruments across interstellar space, and we have already been visited. Here, the zoo hypothesis reemerges with force. If advanced civilizations already know of us, they may avoid direct contact, treating Earth like a preserve. We are observed but not disturbed. From this angle, Oumuamua looks less like a shard of rock and more like a stealth probe. 2I Borisov becomes the control comet, reassuring us with its conventionality. And 3I Atlas, with its close planetary passes and period of invisibility behind the Sun, begins to look like a cartographer at work. This interpretation is unsettling. It suggests that our worlds are being catalogued, our species measured, our planet added to a ledger we did not know existed. Cataloguing is rarely an end in itself. In human history, maps are made not just for curiosity, but for future action. Yet the caution of science remains. Orbital coincidences, no matter how improbable, are still coincidences. Astronomers emphasize that our sample size is vanishingly small. The cosmos is vast. Our observations are young. Perhaps Oumuamua, 2I Borisov and 3I Atlas are nothing more than the first 3 drops of a flood. If so, the upcoming Vera C. Rubin Observatory will tell us its legacy. Survey of Space and Time will scan the entire visible sky every few nights. If interstellar visitors are common, it will find dozens, perhaps hundreds in the coming decade. But if it does not, if Rubin finds few or none, then the 3 we have seen stand out all the more. In that case, the timing becomes difficult to dismiss. Why did the first arrive only once our instruments became sharp enough to notice it? Why did the second appear before we could file the first away as an anomaly? And why does the third trace a route that brushes past the very planets most worth observing? Pattern recognition is not merely a human quirk. It is the essence of survival. To see intent in motion, to distinguish the random from the deliberate, is how species endure. And when we watch these 3 objects skipping across the solar system, one after another, we cannot help but see moves in a larger game. If they are chance, then the cosmos has played a joke of staggering improbability. If they are not, then we are already participants in something vast, a project of observation, perhaps of judgment, whose scope stretches beyond our imagining. Either way, the targeting question cannot be unasked. For once the orbits are seen side by side, the possibility of intention cannot be unseen. And if this is reconnaissance, then the silence of the skies takes on new meaning. The universe may not be waiting to call us. It may already have our file. When scientists look at data, they look for patterns. Noise is everywhere, but meaning hides in repetition. A single comet with a strange orbit is an oddity. 3 in succession, all from outside the solar system, all detected in less than a decade, begins to resemble handwriting on the sky. Oumuamua, in 2017, sliced through the habitable zone fast and enigmatic. 2I Borisov, in 2019, reassured us with its cometary tail and familiar chemistry, proof that interstellar visitors really do exist. And now, 3I Atlas, whose trajectory models place it near multiple planets, as if on a grand tour of the system. Scout, sample, surveyor. 3 roles, 3 moves, each distinct but strangely complementary. The temptation to see design in this sequence is powerful. In astronomy, orbital mechanics are usually the language of accident. Bodies flung outward by gravity, wandering without purpose. But these orbits, laid side by side, begin to look like sentences in a language we do not yet understand. If motion itself is the message, then what is being said? This possibility brushes up against one of the most famous thought experiments in science, the Drake equation. Formulated in 1961, it was an attempt to calculate the number of civilizations in the galaxy. The terms include the number of stars, the fraction with planets, the fraction of those with life, and so on, culminating in the probability that intelligence evolves and communicates. For decades, estimates spanned from "we're alone" to "the galaxy teems with life." But the arrival of interstellar visitors changes the framing. If even one of them proves artificial, the Drake equation is no longer an exercise in speculation. It collapses into certainty. at least one civilization has not only existed, but has sent emissaries across interstellar space. And if one exists, the odds that others do grow exponentially. This possibility also reanimates the zoo hypothesis, the unsettling idea that Earth might already be under quiet observation. The hypothesis suggests that advanced civilizations may treat us as a protected reserve, allowing us to develop without interference while keeping watch from a distance. The zoo does not announce itself to its inhabitants, it simply observes. In this light, the three visitors take on an ominous clarity. Oumuamua as the quiet scout, its acceleration hinting at manoeuvring. 2I Borisov as the normal comet, reassuring us that such bodies exist and keeping our skepticism in check. And 3I Atlas as the surveyor, threading close to Mars, Jupiter and Venus, worlds of special interest in any planetary system. Together, they resemble not random debris, but steps in reconnaissance. If this interpretation is true, then our system has already been catalogued, our atmosphere measured, our biosphere noted, our electromagnetic noise recorded. In human history, maps have rarely been drawn for curiosity alone. They are drawn for use, to mark resources, to define territories, to prepare for future decisions. To imagine Earth as just another entry in a cosmic survey is to glimpse a perspective in which we are not the explorers but the explored. Of course, astronomers emphasize restraint. Coincidences do happen. Orbits can align in ways that look deliberate but are not. Our sample size remains painfully small. 3 visitors in total, but even the most cautious voices admit the timing is uncanny. Why now after centuries of silence? Why 3 and 8 years after none before? Why paths that cut so close to the inner planets, the very cradle of life in this system? The next decade may decide whether this is coincidence or communication. The Vera C. Rubin Observatory, preparing to begin its legacy survey of space and time, will map the sky with unmatched precision. Every few nights it will capture the entire visible hemisphere, watching for anything that moves. If interstellar visitors are common, Rubin will find them by the dozens. The mystery will dissolve into statistics, but if Rubin finds few or none, the questions sharpen. Why did the first appear the very year we had the tools to detect it? Why did the second arrive almost immediately after, proving the phenomenon was real? And why does the third follow a course so suggestive of planetary targeting? This is where the targeting question transforms from speculation into challenge. If we are being observed, then silence itself becomes meaningful. Advanced civilizations may not broadcast radio messages, they may not flash signals in the night sky. Their communication may be presence, objects moving through systems, their orbits the language, their silence the reply. If that is the case, then we are no longer awaiting contact, we are already in it. Contact has happened not in voices but in trajectories, in the improbable handwriting of orbits across our skies. 2 futures lie before us. One, in which the galaxy is crowded with wandering debris, and we are only now opening our eyes. Another, in which the debris is not debris at all, but emissaries, scouts, samples, surveyors, and their presence means we have already been noticed. Either way, the targeting question cannot be erased. 3 visitors in 8 years, all threading through the inner solar system, all carrying implications too large to ignore. Whether by chance or by choice, they have forced us to confront the possibility that the universe is not indifferent to us. And if this is reconnaissance, then the silence of the stars takes on a new weight. For silence may not mean absence, it may mean that the watchers have already spoken, and their message is written in the paths of the messengers they send. The story of interstellar visitors does not begin with Oumuamua, 2I Borisov, or 3I Atlas. Those 3 are simply the ones we were able to confirm. In truth, the record of astronomy contains earlier clues, strange objects, odd meteors, and puzzling orbits that suggest we have been encountering material from other stars for much longer than we realized. What has changed is not the visitors themselves, but our ability to recognize them. When Oumuamua was discovered in 2017, astronomers were quick to note how improbable it was that the very first interstellar object we detected would be so unusual. If fragments from other stars are as common as models now suggest, then we should have been crossing paths with them for centuries. The difference is that until very recently we lack the tools to notice. A telling case comes from 1991 VG, a small object spotted in November of that year by astronomer James Scotty. Only a few meters across, it was nothing like the kilometre-scale bodies we normally consider significant. What caught attention was its orbit, unusually circular, unusually Earth-like, and unlike any asteroid path seen before. Some suggested it was human-made, perhaps a piece of rocket hardware left over from an early launch. Others considered it a temporary capture, a small asteroid that had fallen into Earth's gravitational influence. Yet none of these explanations ever fit neatly. 1991 VG returned to deep space, leaving behind an enduring mystery. In retrospect, some astronomers began to wonder whether it might have been an interstellar visitor, one we were not yet equipped to recognise as such. Another case emerged from the archives decades later. On January 8th, 2014, a bright fireball lit up the skies over Papua New Guinea. At the time, it was logged as just another meteor. But years later, researchers combing through velocity data noticed something odd. The object had been travelling at more than 60 kilometers per second relative to Earth, far too fast to be bound by the Sun's gravity. It was not a local rock at all, but an interstellar meteor. Classified as CNEOS 2014-01-08, it became the first known interstellar object to strike Earth directly. The discovery was so unusual that it required confirmation from the US Department of Defense, which held the classified satellite data that recorded its velocity. Eventually, that confirmation came. For the first time, scientists realized that fragments from other star systems were not just passing through our skies, they were colliding with our planet. This revelation carried immense weight. Unlike Oumuamua, which slipped away beyond reach, the 2014 meteor left behind material on Earth. Expeditions have since attempted to recover fragments from the ocean floor where it is believed to have landed. If found, those fragments would be the first physical samples of matter from another solar system ever collected. For the first time, humanity might hold in its hands not just data, but tangible pieces of another star's story. The list does not stop there. Astronomers have also identified bodies that may have been captured permanently into our system. One of the most striking is 514107 2015 BZ509, an asteroid that shares Jupiter's orbit but does so in reverse. While every major planet and nearly every asteroid orbits the Sun in the same direction, BZ509 moves the opposite way, retrograde, against the flow. The odds of such an orbit forming locally are vanishingly small. The simplest explanation is that BZ509 did not originate here at all. It may have been captured billions of years ago, a permanent immigrant from another star system, locked into a gravitational resonance with Jupiter that has preserved its strange orbit ever since. Taken together, these cases paint a picture of a solar system far more porous than we once imagined. Rocks, comets, and fragments do not respect the borders of stars. They wander, scatter, and sometimes find themselves crossing the paths of other worlds. Earth has almost certainly been struck by interstellar debris countless times throughout its history. Only now are we beginning to notice, because only now do we have the instruments to measure velocities precisely, to track orbits accurately, to distinguish the local from the foreign. The numbers reinforce this shift in perspective. Statistical models suggest that hundreds of interstellar objects larger than a meter pass through the inner solar system every year. Most are too small, too faint, or too brief to detect. They flare as meteors, vanish in daylight, or slip by in parts of the sky our surveys do not cover. The 3 we confirmed between 2017 and 2025 are likely just the visible fraction of a much larger unseen population. This realization carries profound implications for science. If interstellar debris is common, then every one of these objects is a messenger, carrying the chemical fingerprints of its parent star system. Each is a sample of alien geology, drifting freely between suns. Together they form a natural archive of galactic history, fragments from countless worlds scattered like seeds across the void. By studying them, we can learn not only about how our own system formed, but how planetary systems across the galaxy take shape, evolve, and die. But the recognition of hidden visitors also sharpens the tension around Oumuamua. If so many of these bodies exist, then why was the very first one we identified so anomalous? Why did our introduction come not in the form of a reassuring comet like 2I Borisov, but in the form of a silent shard that defied explanation? Was it simply chance? Or does it reveal something about the diversity of objects out there, a diversity that includes both ordinary debris and something more unusual? For now, astronomy leans on humility. The hidden visitors remind us that we have only just begun to look. Our records are thin, our data patchy, our understanding provisional. Oumuamua may be an outlier, or it may be the first hint of a class of objects we have not yet catalogued. 2I Borisov may represent the norm, or it may be only one example among many varieties yet unseen. 3I Atlas may prove to be another comet, or it may deepen the mystery still further. What matters is that the floodgates are open. With the confirmation of interstellar meteors, with the possibility of permanent captures, with the growing awareness that our skies have long been crossed by wanderers, we can no longer pretend that interstellar contact is rare. It is constant. It is happening all the time. We simply lack the vision to see it. The hidden visitors are a reminder that our story with the cosmos did not begin in 2017. It has been unfolding for ages, unnoticed, unmeasured, unacknowledged. The 3 messengers we speak of today are only the most recent chapters in a much longer book. A book written not in words, but in the silent motion of rocks drifting between stars. As our instruments sharpen, the surveys grow deeper, we will begin to read that book more clearly. And when we do, we may discover that the universe has been sending us messages all along. Not rare, not exceptional, but steady, constant, and waiting for us to learn their language. The realization that interstellar objects may pass through our system regularly is humbling, because it forces us to confront how blind we have been. For centuries, even millennia, meteors burned across the skies and comets traced their arcs. But humanity had no way to measure their speeds precisely enough to know which were local and which came from beyond. It is only in the last decade that our surveys have gained the precision to catch such fleeting messengers. Detection is a matter of coverage and timing. Oumuamua was found only because the Pan-STARRS survey in Hawaii happened to be watching the right patch of sky at the right time. 2I Borisov was noticed because an amateur astronomer, Gennady Borisov, had the patience to scan night after night through his custom-built telescope. 3I Atlas was identified through new search algorithms capable of teasing faint motion out of a crowded background of stars. In each case, discovery depended on luck and human persistence as much as technology. The truth is that most interstellar objects are too small or too faint to detect. A rock the size of a car moving at interstellar speeds can streak through the solar system without leaving more than a brief meteor trail in our atmosphere. Unless it is captured on multiple instruments, its interstellar nature is indistinguishable from that of ordinary meteors. CNEOS 2014-01-08, the interstellar meteor that struck near Papua New Guinea, was identified only years later, when classified military satellite data confirmed its extraordinary velocity. How many others have burned unnoticed in the skies, their origins never recognised? There is also the capture problem. Most interstellar visitors move too fast to be held by the sun's gravity. Their paths are hyperbolic, sharp curves through the system, bending briefly around the sun before escaping back into the dark. To capture one permanently requires an unusual set of circumstances, such as a precise interaction with Jupiter or another planet that robs the object of enough energy to bind it to the sun. This is why BZ509 is so extraordinary. Its retrograde orbit suggests that it was captured billions of years ago and has remained ever since, locked in a delicate resonance with Jupiter. Most interstellar bodies come and go, very few remain. Understanding this balance of transience and permanence is critical. The fleeting visitors like Oumuamua flash across our skies, barely studied before they are gone. The rare captures, like BZ509, linger for eons, silent reminders that the solar system is not a closed system, but part of a galactic flow of material. Both categories teach us something different, one about the currents of interstellar space, the other about the ways gravity can weave those currents into lasting shapes. What has limited us until now is not the presence of these visitors, but our ability to see them. The sky is vast and our telescopes cover only slices of it at a time. Even with automated surveys, only a fraction of potential objects can be tracked. Oumuamua's detection, for instance, required not only the right telescope, but the right processing software to flag its unusual motion. If either had failed, the messenger would have passed unseen. This is where the next generation of instruments will transform the field. The Vera C. Rubin Observatory, preparing to begin operations in Chile, will survey the entire visible sky every few nights for a decade. Its Legacy Survey of Space and Time, LSST, will create an unprecedented database of moving objects, sensitive enough to catch faint wanderers that once slipped through unnoticed. For the first time, we will have something close to continuous coverage, a cinematic record of the sky unfolding in near real time. Alongside Rubin, artificial intelligence is becoming an indispensable tool. Algorithms can sift through millions of points of light, spotting patterns too subtle for human eyes. Machine learning can flag anomalies, faint movements, unusual speeds, unexpected orbits that might otherwise be missed. Already, AI has helped identify candidate interstellar meteors in archival data. In the years ahead, it will likely uncover many more hidden in decades of old observations. Together, these tools will reveal whether interstellar visitors are rare anomalies or a constant feature of our skies. If Rubin finds dozens, even hundreds, of such objects in its first years, we will know that the galaxy is rich with drifting debris. If it finds only a handful, then the three confirmed so far will stand out even more sharply, demanding explanations beyond coincidence. Either outcome changes our picture of the cosmos. The prospect of recovery is equally transformative. Unlike Oumuamua, which slipped away, or Tuai Borisov, which disintegrated, interstellar meteors that strike Earth can leave behind fragments we can collect. Expeditions to the ocean floor in search of debris from CNEOS 2014-01-08 may provide our first physical samples of material forged in another solar system. If we can hold in our hands a rock from another star, the distance between worlds collapses. The galaxy is no longer abstract, it becomes tactile. As these efforts accelerate, the narrative shifts from rarity to abundance. The silence of the stars may be less about absence and more about blindness. We were not excluded from the galactic conversation. We simply lack the instruments to hear it. Every new telescope, every refined algorithm, every fragment pulled from the ocean sharpens our senses. And as our vision improves, the number of visitors grows. This realization has consequences beyond science. For centuries, humanity has framed itself as isolated, sheltered in a solar system apart. But the growing awareness of hidden visitors rewrites that story. We are not separate. We are immersed in a current of interstellar material, a constant exchange between stars. What seemed extraordinary is, in fact, ordinary. What we once called anomalies may be the background music of the galaxy. Yet abundance does not erase mystery. The more visitors we detect, the more outliers we will find. Objects that defy categories, paths that suggest intention, fragments that hint at engineering. The ordinary makes the extraordinary stand out all the more. The flood of natural visitors will not explain away Oumuamua or Three-Eye Atlas. It will sharpen them, set them against a backdrop of context that makes their strangeness undeniable. The hidden visitors remind us that the universe is not a distant stage. It is active, dynamic, and present. Every year, countless emissaries slip through our skies, unseen or unrecognized. The 3 we celebrate are simply the ones we managed to catch. The real story is much larger, and it is only now beginning to be told. The arrival of Oumuamua, Two-Eye Borisov, and Three-Eye Atlas is more than a tale of anomalies and speculation. Together they mark the beginning of a transformation in how humanity understands its place in the cosmos. For centuries, planetary science told a story of isolation. Our sun and planets formed from a single cloud of gas, bound by gravity into a closed system. Worlds evolved alone, comets and asteroids wandered locally, and the gulfs between stars remained barriers that no stone could cross. Now that story is breaking. Interstellar visitors prove that planetary systems are not sealed containers. They are porous, open to exchange. Fragments of ice, dust and rock move between them, carried on orbits that pay no heed to the lines we draw between ours and theirs. The galaxy is not a quiet archipelago of separated islands. It is an ocean with currents. Our solar system is one shore among many, washed constantly by tides from beyond. The orbits of these visitors underscore that lesson with clarity. Oumuamua's path cut cleanly through the habitable zone, brushing past Earth's orbit, arcing around the Sun and vanishing outward. In its wake, it left a puzzle that planetary science could not solve, a body shaped like no known asteroid, moving like no known comet. Its course demonstrated not only that interstellar fragments reach us, but that they can thread directly through the inner system, past the very worlds where life arises. 2 years later, Two-Eye Borisov confirmed the phenomenon. Its trajectory carried it inward like a long-period comet, but calculations showed it had never been bound to the Sun. Its speed and orbit revealed its true nature. Another wanderer, this time trailing a luminous tail of gas and dust. For over a year, telescopes followed its progress as it swept through the planetary neighbourhood. Where Oumuamua had been fleeting and silent, Borisov was generous, revealing the chemistry of its parent star system in every plume it released. Its path was not subtle reconnaissance, but a moving laboratory, teaching us that comets are not unique to our Sun. They are a universal feature of planetary formation, and now Three-Eye Atlas charts a course that seems almost designed to emphasize the lesson further. Models of its orbit show close passages past Venus, Mars and Jupiter, each world offering unique opportunities for observation. Near Mars, the thin red atmosphere, rich in dust storms and carbon dioxide, presents a stark contrast to Earth. Near Jupiter, the largest planet, its magnetosphere, storm systems and radiation belts dominate. Even Venus, with its shrouded surface and runaway greenhouse climate, lies on the object's path. Each flyby is an angle, a perspective, a data point in what looks like a survey of inner planets. The fact that 3 visitors in less than a decade have traced such telling courses is what forces a rethinking of planetary science. No longer can we treat the Earth as a sealed cradle, evolving in isolation. These orbits show that our world has always been part of a galactic network, intersected by bodies from far away, carrying with them the chemistry of alien suns. Every passage is a reminder that the boundaries of the solar system are open. This realization revitalizes the old idea of panspermia. Once considered speculative, it now looks like a natural extension of what we see. If rocks and comets can move between stars, then so too can the seeds of life. A microbe sealed within a shard of rock flung outward by an impact might drift for millions of years before colliding with another planet. Shielded by stone, it could survive radiation, cold, and the long sleep of interstellar travel. The course of Oumuamua through the habitable zone, the luminous chemistry of 2I Borisov, the planetary flybys of 3I Atlas, each as a reminder that life need not remain confined to its birthplace. The Earth itself may be both recipient and donor in this process. 4 billion years ago, the young planet endured a barrage of impacts, ejecting fragments into space. Some of those fragments almost certainly escaped the solar system entirely, carrying terrestrial material into the galaxy. Others may have landed on Mars or Venus, seeding them with Earth's chemistry. Conversely, material from those planets may already lie buried in Earth's crust, delivered long before humans appeared to notice. The orbits of interstellar visitors reveal what has always been true. Worlds are not isolated. They exchange matter across unimaginable distances. When 2I Borisov passed through, its tail carried cyanide and carbon monoxide, molecules that play central roles in prebiotic chemistry. When such a body brushes past planets, it leaves traces. Some molecules fall into atmospheres, some embed in soils, some dissolve in oceans. Over time, the steady drizzle of interstellar debris may enrich worlds, nudging them closer to biology. In this sense, the visitors are not only messengers, they are gardeners. They sow the seeds of complexity as they wander. 3I Atlas, with its modelled course past multiple planets, embodies this idea vividly. Each flyby is not just geometry, it is a chance for exchange. Dust from its coma may brush the upper atmosphere of Mars. Particles may scatter into the solar wind, drawn across Jupiter's vast magnetic field. The lessons are not speculative. We see this with comets from our own system, which deliver water and organics to planets and moons they pass. To recognise interstellar objects as part of the same process is to see the galaxy as a web of exchange, where every planetary system both receives and contributes. The philosophical implications are immense. Life may not be a miracle confined to one world. It may be a galactic phenomenon, spread not by intention, but by the natural courses of stones and comets. Each orbit is a possibility. Each flyby is an opportunity. Over billions of years, the probability of exchange rises to near certainty. What we are beginning to witness with our instruments is only the tip of a process that has shaped biology across the stars. Oumuamua, 2I Borisov, and 3I Atlas are visible symbols of that truth. The first moved like no comet or asteroid we had ever seen, reminding us that the universe holds classes of objects beyond our imagination. The second carried with it the chemistry of another star, proving that comets are not local quirks but galactic commonalities. The third weaves through the planetary system as if to remind us that planets are not walled gardens but open theatres. These courses through the inner system force us to see the bigger picture. Earth is not alone. It never has been. It is part of a galactic ecosystem, constantly brushed by wanderers, constantly enriched by fragments, constantly observed, whether by nature itself or by something more deliberate. The isolation we once assumed has always been an illusion. In this light, planetary science itself becomes something new. No longer the study of a single system, it becomes the study of exchange, the chemistry, biology, and history shared across the galaxy. Oumuamua was not simply a riddle. 2I Borisov was not simply a comet. 3I Atlas is not simply a trajectory. Together they are the evidence of a larger truth. The universe is not separate worlds scattered in silence. It is one connected whole. And as we follow their courses past planets, tracing the arcs they leave behind, we are also tracing the outlines of our own place in that whole. Not an isolated planet, not a sealed cradle, but a participant in a cosmic circulation, part of a living galaxy in motion. For half a century, humanity has searched for signals. We built great radio dishes to listen for whispers across the void. We imagined greetings, mathematical codes, cosmic handshakes carried by radio waves. But perhaps we were listening for the wrong thing. The universe may not be speaking in signals at all. It may be speaking in objects. This is the quiet twist in the Fermi paradox. If intelligent civilizations are common, why have we not heard them? The paradox assumes that communication would take the form of radio or laser transmissions. But if civilizations prefer to send scouts instead of signals, then the paradox dissolves. The silence of the stars is not evidence of absence. It may be evidence of a different kind of presence, quieter, subtler, more enduring. From this perspective, the three visitors we've seen in less than a decade take on new meaning. Oumuamua in 2017, silent and fleeting, looks like the advanced scout. 2I Borisov in 2019, luminous and conventional, resembles the control sample, showing us what an ordinary interstellar comet looks like. And 3I Atlas in 2025, with its modelled trajectory brushing past Venus, Mars and Jupiter, seems like a surveyor, deliberately threading a course through worlds of interest. Each plays a different role, each tells a different part of the same story. If this interpretation holds, then humanity has already been noticed. We are not awaiting contact, we are living within it. The visitors are the communication, their orbits the message. This possibility forces ethical questions that humanity has never faced before. If an interstellar visitor is a probe, should we intercept it? Should we attempt to land on it, drill into it, or break it apart to see what lies within? For some scientists, the answer is obvious. Yes. The opportunity is too great to ignore. Project Lyra, first proposed in the wake of Oumuamua, outlined plans for missions that could chase such visitors even years after their departure, using solar sails or nuclear propulsion to catch up. The engineering challenges are formidable, but not impossible. Others argue for caution. If these objects are artificial, they may be designed with purposes we do not understand. To tamper with them might be to invite consequences. A probe could be dormant, awaiting only the wrong signal or the wrong interference to awaken. Or it could be designed simply to observe, in which case our interference would say more about us than about it. The act of taking apart what might be someone else's technology is an act of presumption. In a universe of unknown protocols, caution may be the wiser path. For now, our efforts have been limited to listening. When Oumuamua passed, the breakthrough Listen initiative trained radio telescopes on it, scanning for artificial emissions. The search came up empty. But silence is not the same as absence. A probe may not need to transmit. It could record silently, or communicate in frequencies and forms we do not yet recognize. Our instruments are primitive compared to what might exist elsewhere. To assume we would notice a transmission is to assume too much, and so we are left with speculation. What do they want from us? If Oumuamua was a scout, 2I Borisov a sample, and 3I Atlas a surveyor, then what is the mission? Are they cataloguing planetary atmospheres, measuring biospheres, listening to electromagnetic chatter? Are they mapping oceans, forests and cities from distances we cannot comprehend? The unsettling possibility is that the messengers may already know more about us than we know about ourselves. Their instruments, whatever they may be, could surpass our own by centuries or millennia. They might already have a clearer picture of Earth's interior, a more complete catalogue of its species, a deeper record of its climate. They may understand the vulnerabilities of our planet and the potentials of our civilization in ways we cannot yet see. This inversion, the possibility that we are not the discoverers, but the discovered, challenges our sense of identity. For so long, humanity has imagined itself at the forefront of exploration, pushing outward to map the universe. But what if, long before we took our first steps, others had already mapped us? What if we are latecomers to a dialogue already in progress? The silence of the stars viewed this way is no longer absence, it is presence disguised. Watching, measuring, recording, not interfering, not announcing, but still here. For many, this raises fear. Surveillance implies power, observation implies judgment. To be studied without consent feels unsettling. But there is another way to see it. What if the messengers are not threats, but teachers? What if their presence is not to dominate, but to remind us of truths we're only beginning to grasp. Every one of these visitors has already taught us something. Oumuamua shattered our assumptions about what fragments can exist. 2I Borisov proved that interstellar comets carry the same chemistry as our own, confirming that the ingredients of life are universal. 3I Atlas, with its planetary flybys, emphasizes that worlds are not isolated but open to exchange. Even the hidden visitors, the interstellar meteor of 2014, the strange orbit of BZ 509, have shown us that the galaxy is a place of circulation, not separation. Perhaps this is what we can learn most from them: humility. That our solar system is not unique, that our planet is not alone, that life, chemistry, and even intelligence may be woven into the fabric of the galaxy itself. The messengers may not be here to give us answers. They may be here to provoke the questions we've been too hesitant to ask. And in this sense, what they want from us may be nothing more than recognition. To see their presence not as accidents, but as part of a pattern. To understand that we're not the centre of the story, but one participant in a network of exchange that stretches across the stars. As we sharpen our instruments, as the Vera C. Rubin Observatory maps the skies, as AI uncovers more hidden visitors in old archives, we will be confronted with more and more evidence of this truth. Interstellar messengers will no longer be rare anomalies. They will be part of the rhythm of astronomy, and each one will bring with it the same invitation to expand our view, to think beyond isolation, to see ourselves in a galactic context. This is the reflection that matters most, not only what they want from us, but what we can learn from them. Their courses through our system teach us that planetary science is not local, but cosmic. Their chemistry reminds us that life's ingredients are not rare but abundant. Their silence reminds us that absence of noise is not absence of presence. Their anomalies remind us that the universe is stranger than our models, and that wonder is as necessary as caution. Oumuamua, 2I Borisov, 3I Atlas. 3 names that may echo through history not as curiosities but as milestones. Each one has already changed our science, our philosophy, our imagination. Each one has forced us to confront the possibility that the galaxy is not indifferent. And each one has invited us to learn, if we're willing to listen. So what do they want from us? Perhaps nothing at all. But what can we learn from them? That we are part of a living galaxy, that we are not alone, and that the next chapter of discovery is already unfolding above our heads. The silence of the stars is not emptiness, it is filled with messengers. And the greatest lesson may be this, that the cosmos is not waiting for us to speak. It has been speaking all along, through every shard and every orbit, through every visitor that drifts past. The challenge now is whether we will recognize the language and whether we are ready to learn.